Good afternoon, everybody, and welcome to 5 things you should know about resilience at scale. So, picture the scene. It's 3 o'clock in the morning, and you're on call. And you've just had that dreaded phone call from your 24/7 team that your system has just gone rogue on you, and they want your help to try and fix it. And that's not a great place to be, but I imagine there's 1 or 2 of us in here that's only too familiar. As systems scale and grow over time, behaviours change, different things happen. Over the next 45 minutes, we're going to be talking about 5 different systems architecture areas and sharing some of the things we've learned over the years of operating systems at scale here at AWS. The hope is that you're going to be able to take some of these away and apply them to your systems to make them more reliable and resilient to failure. Or in other words, to try and stop you from being woken up at 3 in the morning again. My name's Nick, I'm a solutions architect here at AWS, and I work mainly with our media and entertainment customers here in the UK. I'm going to be joined by my colleague Danny shortly. He'll introduce himself. So, let's get started. So the first thing I'm going to talk about are dependencies and modes. Now, dependencies are probably something you already understand what they are. They're something that your application uses to give you some sort of functionality. So that could be an AWS service, Amazon SQS or Amazon S3. It could be something you've written yourself, a microservice or some other component. Or it could be something more foundational like DNS or the network. So dependencies in themselves aren't a problem. They're a cornerstone of how we build systems nowadays. But where dependencies meet and interact, well then that introduces some interesting opportunities for failure. So understanding how your dependencies work and behave is key, both when things are going well, but probably more importantly, when things are starting to go sideways. Now, modes, on the other hand, that's a term that's not so frequently used. What I mean by that is when a step change in how an application behaves. So I'll give an example of what I mean. So assume we have an e-commerce application with a front-end fleet, and that talks back to a database. Now, this database holds your product catalogue, so it's something that's fairly static, but that fleet is reading that a lot. It's got a high read workload. So a common pattern would be to introduce a cache at this point. It takes the load off the database and also improves the performance back to that fleet, so that's great. But what adding that dependency on that cache adds the opportunity for a change in behavior, a mode. What happens if there's a bulk cache invalidation, for example? Somebody fat fingers a change, or the cache resets. What happens then? Well, all that traffic is going to fall straight back to the database. Now, if that database is scaled to handle that traffic, say the cache has only recently been put in, well, that's fine. That's all good, it'll handle it. However, over time, as your service grows, that front-end fleet is going to scale out. The cache is going to grow as well. But what isn't going to grow in the same way is that database, because it's being protected from all those scaling signals by that cache. So if we have that bulk invalidation now, all that traffic is going to hit that database. It's nowhere near scaled enough. Therefore, it's going to have a really, really bad day. So that's one way that modes can affect systems at scale in a different way to how that could affect them early in their life cycle. So, enough of the theory. Let's have a real example. So this diagram here, this shows how Amazon Route 53, our DNS service, how this used to look many years ago. So we have at the top the Route 53 API, the control plane. This is where your API requests go in, say asking for, say, a new DNS record to be created, that sort of thing. These requests get put into a database, and then the data plane, the DNS servers that spread around the internet that answer your DNS requests, periodically, they used to go and directly ask the database what the latest updates were. Well, this works, all nice and straightforward. Oops, wrong way, sorry. Over time, as the DNS service grew, the number of DNS servers obviously scaled out. And we started to find that database started to get loaded. And doing some analysis, we found that most of the traffic was all those DNS servers saying, give me our latest updates. So we changed the architecture. So we added a mechanism to take the updates in the database and propagate those into S3. So I did that periodically, and then the DNS servers all picked up those updates from S3. It's great. It takes the load off the database, and it's a great use case for S3. So and this worked really well for several years, many years in fact. So the DNS servers scaled out, S3 scaled out. Again, what doesn't scale out was the database, or not in the same way. There's now no relationship between the number of DNS servers and that database. You can see where I'm going with this, can't you? So one fateful day, that mechanism that did the propagation, that started to fall behind. So the latest updates weren't being pushed to S3. Now eventually the DNS servers realised that we haven't had any updates for a while. So they had a fallback path for that eventuality. And that fallback was the original behaviour, fallback and ask the database, because the database knows. And there we had our modal shift. Suddenly we had all these new DNS servers that are hammering that poor database, which was nowhere near scaled for that level of traffic. So the poor folk on call who were dealing with that first problem of why the database wasn't propagating, now there's enormous other problem of telling all these DNS servers to back off. So this is clearly a modal behaviour, and it's clearly the wrong thing to do. So what did we do? How did we fix it? So if we put ourselves back in the same situation, database propagation is starting to lag, and the DNS servers have just realised that there's a problem. So what they do now is they just alarm. We obviously need to get an operator on the case to try and fix that propagation problem. But what they don't do now, there is no fallback. They don't fall back to the database. Instead, they just continue what they always do, is continue to ask S3 for those latest updates. And if there aren't any updates, well, that's absolutely fine. The other thing they don't do is start hammering S3, asking for updates more quickly because it doesn't know what's going on. It just keeps it on that same regular cadence and just carries on as normal. And what this means is there is a likelihood that you're going to get some stale DNS queries served up, which is fine. It's much better to get a DNS answer that's a few minutes old than not getting one at all. So what we're prioritising is protecting that core data plane service of serving up DNS requests and making sure that continues to work successfully. Now when that propagation service recovers, it'll start publishing to S3, and because the DNS servers are just picking things up as normal, trying to pick things up as normal, they'll just recover. There's no special one-off recovery process with that scary runbook that nobody ever looks at. It'll effectively self-heal. So this is a pattern we've seen on more than one occasion as our systems have grown. And what makes this really ironic is these fallbacks are put in place to try and improve resilience, which they probably do in the early days and systems are bedding in and what have you. But as we've seen, ultimately it does end up harming our resilience overall. So key takeaways from this are to try and identify your modal shifts and try and remove them. So remove those fallbacks if you can. Now there are going to be fallbacks you can't remove. So where you have those, you need to exercise them, and exercise them frequently. You want to try and make your primary path as resilient as you possibly can, but yeah, we have as many systems within AWS that do have those modal shifts. We sort of exercise those shifts as frequently as we can, so it just becomes part of normal operations. So that was modes. Moving on to the next topic, a blast radius. This is a term we use quite a lot within AWS, and by it we mean if something goes wrong, how bad does it get? What's the impact? It's also a bit of a mentality, really. Amazon CTO Werner Vogels is famous for saying, everything fails all of the time. And what he means by that is, rather than concentrating purely on availability, the number of nines, instead we should be trying to consider what could go wrong and design for what can go wrong so that when it does go wrong, we're prepared for it. So to illustrate how we approach something like this. Got a very simple application here. Got a number of Amazon EC2 instances talking back to an S3 bucket. Now, as we've got an S3 bucket being used via the API, it's going to need an IAM policy to give it permissions. So we have an IAM policy that's attached to the role associated with all those instances. So this is all nice and straightforward, probably several nines of availability here. But putting my resiliency hat on for a bit, what could possibly go wrong here? Well, looking at that IAM policy for a bit, what would happen if a change was made to it that, by mistake, revoked access to S3? What would our availability look like then? Well, pretty awful is the answer. There's certainly no nines in that graph. So we deploy that new policy and everything stops working. All the alarms start firing, and because our deployment systems are tied into our alarms, the rollback starts automatically. It's going to take a little while to take effect, but ultimately that rollback is going to take effect and the service is restored. Now that's a pretty bad outage. It's a total outage, so we're going to want to understand how on earth we got to that point. Now, our mechanism for things like that is something we call our correction of errors process, or COE. And in a COE, what we're trying to do is get under the hood of what happened and try and understand what the process miss was that allowed that to happen, so we can hopefully prevent it from happening again. So if we look at our architecture diagram again, the problem wasn't that we pushed a bad policy. The problem was we pushed that bad policy everywhere all at once. So we managed to take the entire system down with that single change. Now, one strategy for this, is quite a common strategy, is to use partial deployments. This is where you deploy a change to part of your system, a small part of your system, and then if it works, you can then roll it out further. So you probably already use this for your code, and we're going to use the same thing today for our policy update. So we've introduced a new policy, that canary policy there at the top, and that's only associated with that canary instance at the top. Those two are sort of on their own. There's also another new policy, that full fleet policy at the bottom, and that's associated with all the other instances. So this does introduce some extra complexity. We now have multiple policies to keep synchronized during a change, but the big benefit it gives us is that any problems with that canary policy or the canary instance aren't going to affect the rest of the fleet. So what would our outage graph look like now if we did that? Well, clearly much better. So here we have the canary policy deployed. It takes the canary instance down, the alarms fire, rollback starts, and the rollback takes effect. So it's still, from the canary's point of view, it's still bad, but from the overall system point of view, things are much better. Now, I have somewhat glossed over a rather important point at this point, is what's causing those alarms to fire? Well, obviously they've got to breach some sort of alarm threshold, but where do you set that? If you set it here, well then things will work as you hope. The failing canary will trigger the alarm and the rollback will happen. However, if we set it here, then if we fail, we push the canary...
The afternoon sessions have now finished. Drinks are being served in the partner expo area.
Thank you. Right, good, right. Right, so yeah, the canary policy deployed and everything's fine. Or is it? So that canary's gone down, so, but we haven't breached the threshold. So when we deploy the full fleet policy, we still take the system down and we all end up on that incident call again, which is obviously marvelous. So during that change, what we need to try and think about is what happened to the availability of the various EC2 instances that were experienced during that change. So the canary instance, we had an availability of 0, but the other instances had an availability of 100%, so that they were unaffected. So the overall system's availability was some number of 9s. Now that number is a function of the number of instances you have. And that's what makes it dangerous to use that as your threshold for an alarm. It's dangerous because that number can change. What could be a really good threshold today, if your fleet now scales out or scales in, that number will change. So what works as a threshold today may not work tomorrow. So a better metric would be to think of that as just the availability of that one canary instance. So as you can see from here, the availability is fairly binary. It's either all on, all off. It makes it very insensitive to where you set that alarm threshold. So yeah, using this as a metric is much better. So we call this a fault boundary. That canary is sitting within its own fault boundary. Things can happen to that instance that won't affect anything within the rest of the system. So try and use your fault boundaries as your availability thresholds. However, it's not quite as straightforward as that. Certainly use your fault boundaries, but equally you still need to monitor the whole system. Imagine if I deployed another policy that allowed the canary to write something to S3 that nothing else in the fleet could read. Well, clearly we'd need to roll that back, but from the canary's point of view, everything is just fine. So we still need to monitor the health of the rest of the system. So when we're making changes, we're obviously trying to minimize the risk of change through testing and monitoring and all those sorts of things. But there are changes that are inherently more risky than others. Things like core network changes being the obvious example. You can test those as much as you like, but you're still not really confident they're going to work first time. So what do we do about those? Well, one technique we use, where it's appropriate, is to deploy change and then immediately roll it back. We don't wait to see what happens. We allow the rollback to happen and then examine the data to see if it's successful or not. So to see how this works, I deploy a risky change and then immediately start rolling it back. Now, just as well, because this change didn't go as well as I'd hoped. But as I rolled it back really quickly, the recovery happens really quickly as well. Probably before the alarms start firing, in fact. Excuse me. So we keep doing this until one day this works, and this change, we deploy the change, it works, but we still roll it back. And then we examine that data, do the analysis, and then, assuming we're confident it's not a one-off, we then leave it in place. So when you're thinking about our architectures, some takeaways from this would be to try and get into the habit of thinking about what can fail, or what will fail. Measure your availability of your fault boundaries, as well as that of your overall system. And also for your highest risk changes, think about how you can minimize the time taken for that to roll back. And also how to make it as reliable. You need these things to be absolutely on rails. So talking about, just sort of elaborating on that last point about recovery time, what we've found over the years is that where we have an availability event that can take a while to recover, there's often a queue involved somewhere in the architecture. Now, this isn't to say queues are bad. They're not. They're great. We have a service called Amazon Simple Queue Service, after all. And we use queues all over the place to decouple systems with different availability characteristics. So what I mean by that is, imagine we have a system here, or a service on the left, this producer service, and that offers stuff up to the queue. And then it can, now it's done its job, it can return success back to its caller, so its job is done. Service 2 on the right here, this will now take things off that queue, do some work with it, and everything's fine. And everything is still fine if Service 2 has a little bit of a wobble. Service 2 is down, Service 1 can still write to the queue and return success. Service 2 will then pick things up off the queue when it recovers. However, what happens if that's a prolonged outage, if there's some deployment problem or some broad network problem? Well, Service 1 is fine. It can write to the queue quite happily and continue to write to the queue and write to the queue some more. Service 2, on the other hand, is still down. It's still not working. So from an availability perspective, Service 1 thinks everything's absolutely fine. It can write to the queue, return success, all's good. But from an overall systems point of view, everything's far from fine. Service 2 is down, there's no work being done, and that queue is growing and growing. Now, from a resiliency point of view, we're going to want to measure that queue. The one measure you can use is the queue depth, how many things that are in the queue. But probably a better metric is one that uses the age of the items in the queue, because that's much more tied into your customer's experience. So you'd use some sort of average or percentile of how old things are. You can then plot that metric, alarm on it, and use it to understand how your system works under failure conditions. So if we do that, we plot that graph, and here we see where service 2 is having that problem. We can see that queue starting to build on the left there, and then a much steeper recovery graph on the right as it can start reading things off the queue. And yeah, the fact that graph is steeper, that slope is steeper, that implies that queue is going to empty over time. Now, if you think I just made that up, this is actually a real availability graph from a real service problem we had a few years ago. It's where a consumer did stop working for a bit. So it's a very characteristic shape of a graph. You can see that it's starting to build up on the left, and then a much steeper slope on the right as the service recovered. So imagine we had this backlog that's built up in this queue. What do we want to do about it? We clearly need to empty it as quickly as possible, as that's preventing our service from recovering. So there are a number of techniques here. I'm going to talk about 2 today, but I'm also going to give you some pointers to some resources so you can dive a bit more deeply into this over time. So the first strategy I'm going to talk about is something called sidelining. So if we imagine we're back in our earlier example, service 2 is running slow and service 1 is continuing to put things on the queue, ultimately we're going to build up a fair old backlog. Now when that consumer recovers, it's going to read things off the head of the queue. That queue is generally in order. So the things that are the oldest items in the queue are going to be the first things to be picked up and processed again. Now in many applications, that may not be what you want. The most recent requests, the things that are happening now, these are directly tied into your customer experiences now. The stuff that's been hanging around in the queue for a while may not be relevant at all. So generally, you'd probably want to try and split these apart. So the way you do that is we'd set a threshold, and anything older than that threshold will get pushed into what we call a sideline queue to hold the backlog. Now, the consumer process, its main job, its primary task, is still to process that normal queue. That's now an awful lot shorter. But the consumer also now has a secondary task, a lower priority task, to go and process that sideline queue. Now, it may need to scale up to do that. It may still take a while to do that. But in the meantime, it's now processing all the new requests when they come in. Now, a variant of this is that you can just delete the backlog. Now, this is obviously not universally applicable, but if it is, if you could use that technique, that's going to dramatically improve your recovery time. So that was sidelining. It's useful if you're able to defer or even avoid processing the backlog. And it's doing that in favour of getting recovery back to as quickly as possible. But what if you can't do that? What if you've got to process all of the messages in the order that they're arriving? What do you do then? This diagram here is a sort of abstract view of how many of our AWS services are architected. So we have the control plane service at the top where the API calls come in, very similar to our Route 53 example earlier. And then those requests effectively put in a queue. And there's a propagation service then that's responsible for taking things off the queue, processing them, and then pushing them out to the various data plane services that actually implement the service. If that propagation service becomes impaired in some way, then that queue could potentially start to build. Now, if you're thinking about a service like Amazon VPC, these messages, these requests, are going to be things like changes to security groups or route tables and things like that. So important things, they've got to be handled in order, and you certainly can't throw them away. So sidelining isn't an issue. So what the VPC team did was use a different technique called back pressure. So here, if the propagation service is impaired, things build in the queue, but only up to a point. It's not allowed to grow indefinitely. So it effectively becomes a bounded queue. Now the control plane is also monitoring that queue, and if it sees that queue start to become full, it then starts failing customer requests. Now this was somewhat controversial, as I'm sure you could imagine at the time. What do you mean failing customer requests? We don't do things like that. But what we're doing here is trading off availability, the number of nines, against resiliency, The aim here is to try and make that recovery time as quick and predictable as possible. Remember, we can't allow a backlog to build up because it could take hours to build through, and we've got to process every last message. So takeaways from this area are know how to spot queues. They're not always called queues. They could be rows in a database or log files. And it's basically anything that could build up a backlog. To have metrics on your queue, how old things are on the queue, but probably more importantly, know how fast it takes you to drain your queue, as that's key to knowing and understanding your recovery time. And then finally, where you need to, have a bounding strategy on your queues to avoid a huge backlog from building up. Now, I did say I would give you some resources. This Amazon Builders Library article on unbounded queues is excellent, written by a colleague of ours, David Janacek. He talks about a number of different strategies for managing queues, including the two I've touched on earlier. So with that, I'm going to hand over to my colleague Danny, who's going to round things up with the last two topics. Thank you.
Cheers, Nick. Okay, errors. So you probably have all seen errors all the time as part of your working day. You may see errors when you're calling an AWS service. You may also see errors when you're calling some kind of dependency of your own. And per the RFC, they're pretty much organized into these two quite important categories. So we've got 400s, they're our client errors, and 500s, server errors. Now, you'll see both of these, but I'll wager that you see a lot more of those client. .500s, we see these less. So there was something server side, and it's not your fault. There's no direct action that you can take, and if you come back later, it's probably going to work okay. And we see both of these types of errors in our world at AWS. In fact, here are a couple of graphs showing 400s and 500s. I'm just going to give you a second to try and figure out which one you think is which of these. So I've been a little sneaky. I've switched them around, some of you might have noticed. So now actually on the left we've got our 500s, and on the right we've got our goes bad, there's some automation that takes that host out of service. It takes a little time for that to kick in, and so you're going to see the odd error coming through. Now, our 400s, we see a lot more of these. There's something wrong with your request. You know, perhaps, and I'm sure this has never happened to anybody here, but maybe somebody messed up their IAM policy. They forgot that ever important line in there, and they got a 403, right? It happens. So we see a lot of these 400s. So why does the difference matter between the two? It actually matters a lot for availability, specifically for your ability to detect . When things are going wrong. So it's not really telling me very much. I don't really know from looking at this, like, is my service failing or is it actually succeeding? This is kind of what a 400s graph is supposed to look like. So you can see we've got a bit of a pattern. You can see that, you might have guessed actually, we've got a week's worth of 400s here. You can see that weekly diurnal pattern going through. And so that's why it's really important actually to classify the two, because one of them is a source of signal and the other is a source of noise. You don't want to fold signal into your noise, and you don't want to fold So let's doctor in another outage with 400. So I can see I've got something to look at now. It's pretty clear. And so what is this telling me? It's actually not telling me very much still. Like, I still don't know what's going on here. Could be a couple of things. So, scenario one, perhaps we had some kind of bad deployment. So imagine we pushed a configuration and inadvertently some limit, some kind of max value of some parameter, we accidentally made that lower. So requests that were succeeding before are now failing. And as a service owner, like, that's your problem. Like, you've got to go fix that. You've got to make that better. The other option is maybe it's just a customer getting like really over enthusiastic, making wrong calls, like a Well, the way you get an event to end is time to detection plus time to mitigation. Like knowing there's a problem and then mitigating the problem. And so getting the most signal that you can out of the errors that your service is returning is actually how you get to shorter outages. And I love this connection. It's kind of non-obvious, that link between the two. But yeah, really important that that code is classified really cleanly. So 500s might need your 500s need your attention, 400s might need your attention. All right, let's take a look. If my service is a monolithic unit and this is a percentage of my overall availability, then I do agree with the nice chap in the stock photo, like we're doing okay. But what I want to ask is, exactly whose 9 was that? So the thing about running services at scale is you might actually have an architecture like this, where you're directing or sharding customers into these different instances, cells, like a cellular-based architecture. We use this all over the place at AWS. It gives us a known, contained, anticipated scale. And so the thing is, the graph that we were looking at before, what we were looking at is actually an average of all of these customers in their cells. And when you take an average of something, you actually lose a bit of the fidelity of what you are looking at. So what's really important to do actually is to measure these separately. So if we are to measure these on our graph, now we can see that the customers who are in our blue cell it's really important that we actually measure these separately. Another feature, we love this inside AWS, it's CloudWatch Contributor Insights. So we talked about that top talker scenario earlier. This is something that would really help identify that. So here I'm showing 400s by account for a very large scale services. You can imagine there's a lot of customers that we have at AWS using a particular service. And here we get some quite unique insight into how those customers are using that service. So if I'm looking at our blue customer there, they're having a fundamentally different experience of our service than everybody else. So why is that? We've seen everything. It could be, perhaps that customer is running a load test and they are running into errors deliberately, like they want errors, and they're running that at a very, very high rate. That could be one thing. Another thing, maybe they have misconfigured something and they actually don't know. Interesting to look at too. So 400's not entirely useless. They're actually telling you a lot about the way that your customer is using your stuff. Okay, errors. So matters so much that you're able to cleanly classify that signal and that noise, and so that you're able to get to the issues that really matter, those 500s, as quickly as possible. It's going to give you quicker time to detection and ultimately shorter outages. 400s, still a useful source of information because they're telling you how people are using your service. All right, our last topic of the 5 things today is going to be retries, and this is closely linked to our topic before of errors, because if you get a 500, you should retry. So here we have a client and it's calling a service that is temporarily unavailable, unreachable, and it's throwing a 500. So not very happy about that, but it's not my problem, it's their problem, so I'm going to retry. And that's still not working, but people quite like the number 3. It's got some nice symmetry, so I'm going to retry again, and I got a 200. Everything's okay. Now, if this API was perhaps on an AWS service that you call in, then you're probably using the AWS SDK. The nice thing about the SDK is actually a lot of time has gone into implementing really good retry behavior there. So in all of the languages that it supports, you get that kind of out of the box. You don't have to think about it too much, configure too much there. And it's got all those good things around jitter, back off retry, that's all baked in there. But what about if you call in a dependency of your own? Then implementing that retry behavior is actually pretty important. So here's another thing about retries and services at scale. So here we've got a couple of services, and when you're getting faults, when you're getting retries, it's because something's gone bad. So here's 2 AWS services where, for a brief moment of time, we've had some kind of impairment. You can see along the bottom of the graph there, we have our faults depicted in green, and the inverse of that, we've got our requests coming into the service. So these are 2 different AWS services. In faults, you will receive more load. And this is kind of like a mode, like Nick discussed earlier. We're in retry mode now, and it's not really something that you can avoid. It's like a law of physics sort of thing. So when your service is throwing faults, you're going to get more load, and you can't get out of it, but there are some things that you can do to make it a little less challenging. So we're going to build a microservice architecture now. So service 1, call service 2, call service 3, call service 4. And we're going to talk about, not if, but when, service 4 has some kind of availability event. So we got all the way down in our call chain to service 4, and service 4 is having some kind of issue, so they're throwing 500s, okay? But service 3, we're configured with the right retry behavior there, so we're going to try again. Still not working, we'll try again. Still not working, and at this point, service 4, they're having like a prolonged outage, and so service 3 is now having to turn around to service 2 and say, I'm sorry, I was not able. You can see this starts to build up pretty quickly. And this is a little bit of a caricature of how this works, but it really does work like this. You get this amplification of retries along the way. And so poor old service 4 on its worst day, is now potentially receiving an unprecedented amount of load in there. And what do you think that's going to do for Service 4's ability to recover from that outage, even when the lights do come back on? So how do we wish that this works? Maybe we wish that it actually worked like this. So maybe if Service 2 and Service 3 were aware of their intermediate status, and actually we let Service 1 drive those retries, maybe this would do a little bit better. So which one do you think is going to recover more quickly? The one on the left or the one on the right? So it's probably going to be the one on the left, because it's the one that's not receiving, huge amounts of load. And so I just said, maybe Service 2 shouldn't drive those retries. So here's the thing, there's a human factor involved here. These are different microservices. They might have their own 2 pizza teams, and they've got their 9s to think about. And actually, maybe Service 4 takes these little hiccups every now and again, and this retry behavior has actually been helping Service 3's customers skate over those issues, so it's been doing quite well for them. So if we let Service 1 drive those retries, from Service 3's local perspective, this is worse. They're going to lose a 9 there. But if we think about it from the global perspective of the service, actually, quicker time to recovery more important than our 9s. And as Nick said, we're going beyond the 9s here, and actually what's more important for our service as a whole. So another thing that we think quite a lot about is throttling, rate limiting. So if you find yourself in this picture on the right, this is your best way out of this problem. Actually throttling the amount of requests coming into your service to allow the service to recover. Now again, it sounds bad, we're pushing customers away here and we're maybe losing some 9s, but that quicker recovery might actually mean some of those retries actually succeed. Okay, we're going to finish on a DNS example. Started on DNS, let's finish on DNS. So I painted retries as a little bit of a villain there, which is not entirely fair because they do help us skate over those issues, but they do give us a modal behavior. So what about if you want retries, but you don't want the modal behavior? So here's an example from our DNS infrastructure within EC2. So we have something called Route 53 Resolver. If you know your virtual private cloud concepts, that's your .2 address in your VPC where by default DNS queries go to get resolved. Now DNS from an EC2 instance's perspective, pretty important, right? DNS has to work. And so what do you think is going to happen if perhaps one of those resolver hosts goes bad? Well, that EC2 instance, it needs to do what it needs to do, so maybe we should retry that. So here's the problem. We've got a lot of EC2 instances running in the AZ. So what would happen if, perhaps a bad deployment, something that took out, multiple resolver hosts simultaneously, are we going to actually 2x the DNS traffic in the AZ? That's going to be a bit of a surprise. That's going to be a mode. We're going to be in a very specific mode there, and that's going to be a real surprise to all of the infrastructure that we have there in the AZ. So how do we have our cake and eat it too? So the way this works today, and this all happens under the hood, it's not something that you see, but when you're making a DNS query to one of those resolver hosts, you're actually going to 2 at the same time. And whichever one's quickest, you get the response back. Maybe one of them's acting a little slow or it's gone bad. You get it from the other one, you don't even notice. Now, there's a trade-off to doing this. We're effectively running twice the amount of DNS traffic in the network at all times. So you have to pay some scale for this, but for something as important as DNS for EC2, it's actually worth the trade-off. So proactively retrying all the time. A little bit of a niche example, but this is something that's been really effective for us. Okay, so retries, they sound bad and they drive additional load to your service when things are already going wrong. But there are some ways that you can deal with that inevitable additional load. And if you want retries but you don't want the modal behavior, perhaps just try retrying all the time. All right, those were the 5 things. My hope for today is even if you have a lot of experience, you learnt something new today, perhaps you looked at something in a way that you haven't looked at it before, We talked about blast radius and how important it is to segment, and so the changes that you make are limited in the scope of impact that they can have. We talked about dependencies and modes and how the way to deal with a loss of a dependency is not to completely shift modes. We talked about queues, which, if you think about it, are blast radius along a time dimension, and ways to deal with that backlog. We talked about errors and that unexpected connection between how cleanly classified your code is and getting to shorter outages. And we talked about retries and that inevitable extra load that they're going to drive into your service. So I'd like to direct you all to our Skill Builder service if you want to learn about this topic and more. Last of all, I want to thank you all for your attention today. Me and Nick have loved speaking to you about this topic. I hope you enjoy the rest of the summit, and safe journey home, everybody. Thank you so much.